machine learning looks like in practice. And thinking about what I kind of wanted to talk about today, I thought about my learning journey as I became a data scientist and through school, and how things seem to be a lot different when I was in the classroom versus when I got into actual problem and application areas. And so I wanted to talk a little bit about some of the pitfalls that people can fall into, one can fall into, perhaps I was the one that fell into it, the pitfalls that I can give you some advice on how to avoid, and give you some insight into some really great ways to make great models and understand their performance. So before we jump into that, I just wanted to say I do have a dog and I have a cat and I have a new kitten. Things might get a little bit crazy. Please just excuse me for those moments, but we will try to make it through. Also, here she comes right now. Also, my computer can be a little bit temperamental. So just stick with me. We'll try to make it. Okay, awesome. All right, let's see. So today, as I said, we're talking about machine learning and what it looks like in practice. I know a lot of people are coming from an R background. Some people are coming from a statistics background. If you guys wouldn't mind, I'd love to get an understanding of that right quick, just to see. Is anyone coming from so put a thumbs up if you're coming from a programming background. So if you've had like a lot of experience in like computer science, or you're like an electrical engineer, or have just done a lot of coding in the past. Okay, I'm seeing a few, Finance, okay, gotcha. What about people coming from something very statisticsy? So if you feel like you just have a really amazing background in statistics and just know all about the different types of p-values and all that great stuff, why don't you go ahead and put a thumbs up as well? All right. Let's maybe a little less confident here on the stats. All right, well, stats, not confident people, you should feel very welcome at this workshop, because that is what we're going to talk about. We're going to talk about R a lot. And the reason is some of the work that's been done in R is so well laid out and well explained that it's easier to understand coming from that point of view. So anyway, without further ado, now that I know a little bit about you guys, let us get started. So last time, if you came to our last workshop, you would have seen this slide. I stole this directly off of Jesse. So thank you for that, Jesse. But this is the basic set of stages that a machine learning and data science projects go through. So of course, as you know, we always start with the problem definition. We try to get a really great understanding where we're trying to go, what we're trying to do, what it means in terms of metrics, what it means in terms of your application area. From there, we tend to do a little bit of EDA, kind of understand, what's the data like. When we start modeling, that helps us understand what we can expect from our models and how they could perform. Then we get into this loop, right? Feature engineering and modeling and assessment. And we tend to do this really, really iteratively. So we can continually improve our model. Let's see it get better. Sometimes see it get worse, of course. Try some new things out and try to come up with the best predictive model. Okay, so after that, so we kind of are not doing the deployment part. We kind of really sit in the data science realm of trying to generate predictive models. But you tend to think about this circularly. So you do these things iteratively. So this is a wonderful picture, and it gives us a really great overview. So let us talk about maybe what this means specifically and practically. All right. So I guess I'm kind of just stealing things from everyone today, but I stole this off of H2O's website a really long time ago, maybe a year and a half. And the way that they break down machine learning is as so. Okay, so very similar stages that we had before, but they say first you formulate the problem. Okay, perfect. That is what we're used to doing. That's what we had on the last slide. Then in this data processing phase, we clean, we transform, filter, aggregate, and impute during this data processing phase. So it seems like one single phase where you do it once, and you do all of these things and operate on the data. So cleaning, that would mean that you might be like changing things within your data set to make them more correct. So maybe, you know, people have different capitalization on the same kind of name. Transforming might be converting one type of data to another. Filtering might be just taking some things out. Aggregating is putting things together, and then putting in values for, you know, missing values. So those are the things that it seems like we're doing just kind of one time, and then the data is kind of done. We're done processing it. And then we just convert that into our X and Y, meaning we're going to convert that into our predictor set. And then we're going to convert that, part of it, into the outcomes. Okay, so we have a row of predictors and then the outcome that relates to those, and those will be your full data set. Okay, so that's looking good. So I think we talked about how that looks with H2O flow. Then it looks like we're going to go and we're going to start doing machine learning. So we're going to take this thing that we had, this X and this Y that's been done and processed, and we are going to start training models and evaluating those models. Wonderful. All right, so let's just try that out. Let's try that out. So we're just going to follow the steps, like we're going to try to follow them exactly, right? So we're going to start out with our data. As we said, we have our X and Y. Okay, so this blue block, this is the data that we have. We've done the things that were said. All right, so we have our X and Y. And then we're going to decide we're going to do our machine learning, right? So we, let me see. Sorry, we're clicking here. Computer's not believing me that I want to move forward. All right, so we're going to train our model. So in this section, what we're doing is training the model. This little green box means we're training, this green box is the trained model, okay? And we are training it on this X and Y data, right? So this data that we have cleaned and transformed one time, all of it. Good, because that's what these lines said to do. So then we're also going to evaluate the model as these lines also say, and we're going to use that same data that we had and process once. Great, wonderful. So we do that. We get some metrics back, and we expect that whenever we're done training this, so training on the same data, evaluating on the same data, when we go and we apply this model to other data, we expect that the performance will be just as good as this, right? That's how it should work, right? Wouldn't that be awesome? So, we have this performance and we have this final model, and we expect that it's going to generalize because we've trained and tested on the same data. How many people think that that sounds right? So if you think that it sounds right that you should be able to train and test on the same data, and then the performance on data that you haven't seen at all would be the same as that data that you've already seen, as that performance that you've already seen, go ahead and give me a thumbs up. If you think that maybe that you might do a little worse on things that you haven't seen in your life, or your model hasn't seen in your life, then go ahead and put up a group, well, let's see, red X. I think that might be a, yeah, some people are in disbelief. They're thinking that, you know, the generalization is not going to happen. There's going to be some raggedy results. Yes, the model may do worse on test set over training set, and it probably will. So that is some great insight. You guys weren't believing me for a second, were you? You're like, this girl, she is seriously telling us that we should train and test on the same data? How awful. I'm just going to leave. I would never tell you to do that. That's awful advice. Don't do it. And yet I actually have seen people do this in practice. So again, the reason that I'm talking to you today about these specific things is because I've seen them, and I want us all to be able to avoid these pitfalls. Okay. So again, the pitfall that we just saw, we trained and tested on the same data, and we thought that the performance was going to be great. It will not. Okay. So that kind of raises the question then, how can we fix this? Does anyone have any thoughts on how one might get around training and evaluating on the same exact data and then understanding the performance? Love those ideas. Ooh, man, you guys are just on the ball. So it seems like people remembered what we talked about last week. So we like to split the data. Okay, I like that. I like that a lot. And again, we said that the problem here was that these things are the same thing. So this X, so this and this is the same thing. So this is going to be a little bit worse than we expect on the training data. So people said, okay, we're going to split into training and test. 70-30 split, random split. These are great ideas. There's a lot of different ways that you might, or different ways and different reasons of how you might split the data, and that will be specific to your application. So do think through that. I think tidymodels has, a great book, and it talks about like the ways that you might split the data. So I would suggest that. Oh, Aaron. So I think you are capturing where I was thinking about going. So let's say, how do we think we're going to fix this? So there's many ways, one of which is deciding that you're going to split your data, but maybe you decide at this stage that you want to cross-validate. Thank you, Melissa. That's exactly where I was going. We've decided that maybe what we'll do is cross-validate. And cross-validation is a type of resampling. So you see that word here, resampling. There are lots of different types of resampling methods, okay? So in all of my machine learning classes, I think the only resampling methods we talked about were k-fold cross-validation and maybe Monte Carlo resampling. There are lots of other ones, including the bootstrap, for example. Statisticians love bootstrap, could be interesting. Give that a read. Again, there's a great book on feature selection and modeling by Max Kuhn. It's right there in my bookcase. Great, gives great overviews of the different types of resampling methods. And they all have their pros and cons. People that are coming from computer science really do think about the k-fold cross-validation. A lot of the statisticians think a lot about the bootstrapping. Really, it's, for me, when I think about this, the book, Jesse, would you mind putting the book in the chat? I can see it. It's like right over there. It's a little blue. I think it's actually Jesse's book that I happen to take from work. Stealing things more. Okay. But yes, there's lots of different resampling methods, and they all do have their pros and cons. But a lot of people do really like k-fold cross-validation. So whenever you see it later today, it's going to be called v-fold cross-validation, but it's still the same thing, okay? So this is that type of cross-validation that we're talking about. Basically, you saw before that we had the data, so it looked kind of like that. It was that X, and we just snapped it together with Y. So like this, there's no real difference there. But what we do is we take it and we divide it into different folds. So now with k-fold cross-validation, what we do is, for example, we're going to have this training set here of fold 2 through k. So we're going to take that subset, we're going to train on it, and then we're going to test now on this fold 1, okay? Right? So that's going to give us some performance here. Then we're just going to repeat this a bunch more times, holding out each fold and testing on that fold. So for example, now we're going to take fold 1, 3, 4, and k. We're going to train on those, and then we're going to test and get the performance for fold 2. And so now after we've done that, we actually have kind of this small distribution. And again, distribution, the word distribution is why people like these different kind of resampling approaches. This has literally 5 resamples, which is, but it can give you a good overview of what's going on. So now we have these 5 resamples. We're better off than having just used the training data, and we're better off than just having used just one other extra set of data. So now we have some understanding over a bunch of training and testing iterations of how things are going to go, right? So that's pretty good. That's good news. All right, but so this is the point of consternation. So now this green box is supposed to be the model, right? So now that you've done this k-fold cross-validation, where is the model that you would actually use or predict with? Like where is it? Does anyone have any thoughts on that? Totally understand why you don't have any thoughts on that, because it's kind of nowhere a little bit. It's kind of nowhere. So you actually have to generate this. So after you've generated models on these different folds, which you actually have are 5 different folds. These are fold models. And then what you would do is you would train now again on this regular data set here. Whoops, might have clicked too many times. Okay, now we train this on the data set, and now we can also evaluate however we are thinking. So once we have our k-fold cross-validation measures, that actually tells us about the model performance, okay? So something interesting here that I really came to appreciate greatly is that this is really great for model selection, right? So let's say that you're trying to decide between like 10 different models. So a model being either a different type of model, so maybe not a linear model, maybe not a decision tree, maybe not an ensemble, maybe not a neural network. So maybe you're trying to decide between those, but maybe you're also trying to decide between different like hyperparameters that influence that behavior. So for example, random forests are made of trees. How many trees? 5, 5,000, 5 million? What about short trees? Do I really want like a bunch of bushes, or do I want cedars? Like what kind of trees do I want? So by actually using this cross-validation strategy, we can build a model of every type. So whatever hyperparameter of whatever category, and we can compare them like as distributions instead of just single numbers. So this is a very, very cool situation to be in. And the third part of this cool situation to be in is the fact that you have only actually used your training data. So this is only on training data. There's no separate piece of data being used to evaluate which model you should pick. It's only coming from this one little bit of data. So that is very cool. So just a moment ago, I talked about this kind of analysis. So after you train the model, you can actually look, I think what is it called? There's like 2 terms for it, where you just run your model back on the same training data that you have. I often do this, but it's really not a good predictor of like how your model is going to generalize. This is what you want to use. So I don't know if you can see these. I just realized that you can't. What these are is these are just a set of metrics. So we use our model and we look at all the folds and how they predicted. And from there, we can calculate things like accuracy or precision or recall, and we can get the mean of all of these measures. And that'll help us to understand the generalization. If we were instead to just predict on the data that we had, so our training data, that would just give us kind of an understanding of how the model trained. So this gives us a good like kind of thought process around how the data in the model is training, but this gives us a good understanding of the generalization capabilities. So what are y'all's thoughts on that? Does that make sense? Is that feeling reasonable? Is it feeling reasonable? All right, good. Things are feeling reasonable. Sorry, my cat is like, she is just scratching me, my ankles. Okay, so good. I'm glad that sounded good. However, there is still some struggle here, okay? So we talked about our desire here to generalize, right? And this gets at it like a lot, like it gets at it a lot. But if our goal is truly to really generalize, then what we really want is to have a different framework. I was going to tell you the answer, but actually I think you guys will have the answer. So what are your thoughts on how, so this is just the entire data set. We've now taken this entire data set and split it up into folds. But if we wanted to have maybe a understanding of how something would work without having seen any of the data that we've ever looked at, what might we do? Okay, I like that. Ooh, I like that too. Runs lots of versions of the model and get the average. Yeah, I'm with you there. That's getting into kind of a little bit of the K-fold cross-validation. I think your mind was with me before when you guys talked about, beautiful. Thank you, Jonathan. Great. We talked about splitting the data. So we said what we would do is that we would split the data into a train and a golden holdout set, right? Split. Training and testing, right? And that makes sense. So how could we do that? We just split it right there. Great. Now we have this blue box here. We're only going to use that and do everything we just talked about, do all that good resampling and the strategy that we like. And then we're going to compare across different models that we're interested in. We're going to select one. And then we'll finally see the performance of that model on our golden holdout set. And the reason that we don't like to just use the evaluation of the golden holdout set across all of our models, which is something we could do. The reason we don't like to do that is because once you start using your holdout set a lot, it actually has just become a part of the modeling process. Like you're making decisions based on data that you weren't supposed to have seen. So now you have seen it, and now it might as well be in your modeling framework. So you really want to wait until the very last to try to pull out your training data. or testing data, sorry. Okay. So anyways, this is still working. This is still making sense, okay? I think we're all on board with this framework. I think this makes sense to everyone. However, there's always something. However, there is one little problem here, which is a piece that I think many people don't think about a lot. So this is still problematic. I only recently, not recently, but like maybe some years ago, saw people really starting to talk about this in depth. Okay, so this is still problematic for us. Does anyone have a thought about why this might be problematic? So this is essentially saying that this is some data of some origin that has been processed, right? And now we're doing all of this resampling on it and we're training and testing on it. Do you see anything wrong with maybe what this like data might be? Have any thoughts about that? Oh man, there are some great thoughts in here. Okay, maybe the original data is not representative. That is actually a really great point. I love that. That's a huge deal. But that's something that you kind of have to, you would have to work out. Let's see, your holdout set might not be good. Depends like good. Yep. If there's a time, okay. Yep, I'm with you. These are really great things to be thinking about. Those are really great things to be thinking about. Yeah, that's a huge deal. Though, but there's something even more nefarious in here. And it's kind of what we were talking about when we looked at that little box about modeling with H2O that they had written. And they didn't probably mean it in this way, but this is how many people would read it, okay? This is how I have seen many people read this, okay? So let's look and see why the situation is problematic. The reason it's problematic is because you just don't arrive at data. Many things come before you start processing your data or you start modeling with your data. So you would have still like split the data, which would have made sense, but you would have split the data after you've actually done a lot of pre-processing on your data. So imagine this, roll all the way back to the beginning. The data lands on you, right? Okay, you start processing things. Things are looking fine. You're careful because you don't want to, like you do sometimes look at all the data, but you really want to try to focus on only really using the training data that you split, okay? Okay. So then you start looking at your data and you're saying, all right, well, I'm gonna have to model at some point. Let me take this whole data set and I have some variables which are categorical and let me encode them according to everything that's present in this whole data set, okay? So it's interesting. That could potentially be problematic. It's okay though. Let's see, log transform. This one might be safe because it is just a computation on a number. It doesn't depend on anything else. Imputing missing values. Imputing missing values. Oh, I see someone mentioned that there in the chat. So how do you impute missing values? So a lot of times what you do is you take whatever data that you have available. That's it, Shalini. Sorry if I just massacred that. Mean, median. You take whatever is in that column that you have, you take the mean of it, and now, or the median, which is better, and you take it and whatever missing values in that column, you just poke it right in. Just pop it in. Okay. So now, again, you're using this on the entire data set. The entire data set. Okay. Okay. Well, okay. We'll continue pondering that. So we also do know that there are some models that require normalization. So like logistic regression. So now we're taking the entire data set, we're taking a particular feature and we're going to normalize it. So what do we need to normalize a piece of data? Or not a piece of data, but a set of data. What kind of numbers do we need? Yep, we need the mean over all of those values. And we will, yeah, that's it. Well, we will need estimates over our entire data sample. So just not sounding good, is it? Because what we've done here now, after we're done normalizing the data, using all of our data, After we're done doing all this categorical encoding and the imputation, and also some feature engineering, just depending on if this is specific to your purpose, you may end up using information now in your test set, right? So you have all the data, you're doing all this work, and then you split the data. So once you have split the data, you have already normalized all your training data based on this test data that you should have had. You have imputed missing values using the mean from values that you shouldn't have had. You have done this thing called data leakage. And so these are the specific ones that tend to introduce the worst issues, depending on how you're going to be doing your feature engineering. Log transform, you can kind of ease that one out because it's like a computation that it doesn't depend on the other values. But these do depend on the other values. So you have to be really, really, really careful about what you do and when you do it, and to what pieces of data, okay? So, seems I see some nodding heads here, so I think you guys are on the same page with me. That's sounding good. How can we fix this problem about pre-processing the data and then splitting it? How can we fix that? James, you're on the ball today. Perfect. So it seems like you would split the data first then. So you don't split it here, you split it out here. Okay, so let's try that. Okay, so we have actually the same thing that we had before, except we put this back. So this is like some larger piece of data, which we will define in just a moment here. Okay, and then we're going to separate this original raw data now into the training data. You see here, and then the testing data. So now we're doing a lot better, right? So we just have the training data. We are now going to pre-process everything that we have only from the training data. We're going to impute only from the training data, normalize only. It's great. Things are great here. We're going to train. So we're going to split this into X and Y. Training data, great. K-fold cross-validation, resampling, great. Pick the best model, hyperparameter tuning, great. Train the model, get the performance, great. Things are great. Life is looking so good. Okay, so what happens then now that we have our trained model? Well, we use it. And the way that we use it in this framework is quite interesting. Okay, so now, again, what we're trying to do is we're trying to evaluate on this golden holdout set. So now, remember, we've already done all this good stuff. We have looked over like 10, 12, however many different models. We've picked maybe the last one or maybe two that we're going to look at. And we're now going to evaluate them on this golden holdout set. Okay, that's what we're doing. Mahmoud, that's a good question. And let me come back to that in just one moment. Okay, so now that we have our final model, we're going to take this test set. Okay, this test set is unprocessed, right? So what do we need to do? Well, we take the parameters that we've now estimated from the training data, and we would apply it to the test data, right? So you had to impute something, right? You had to compute some mean. You had to figure out what that was. We're just going to use that now on this test data. We had to do some kind of encoding. We had to do some kind of normalization. We're going to use all those different parameters we estimated from the training data, and we're going to use them to pre-process our testing data. Okay, great. It's amazing. Okay, so now that we've done that, we just go on with our current strategy that we always do. So now we get our trained model, we use this data that we pre-processed, do some prediction, and analyze how we've done. Hopefully it's absolutely amazing. This right here, this setup is not bad at all. This is actually, I think up until last year, I think this is actually the framework that I saw the most, how people tend to train their models and understand their performance. So it's not that bad. Also, Mahmoud, that's a good question. So you said, why is categorical encoding before splitting a problem? So it both is and isn't, depending on what is happening in your data and what you expect. So for example, let's say that, let's say you have a really imbalanced training set or a data set, really imbalanced on some categorical variable. So it's you split your data, and actually in your training data, you never see a specific category. Okay, so you've never seen, I don't know, I love plants, so I guess now it's time for me to talk about plants. So you've never seen a ficus before. That's not in your training data. So now you go and try to predict. You should actually not really know what a ficus is. So when you see the ficus in your test data, you should not actually be able to say that's a ficus because you've actually never seen a ficus. So that can be an issue. Oh, iris. That would have been better. I should have said iris. But that can be an issue. Like, so what you should predict there should be something like, I'm not sure, something novel. And we start talking about tidymodels, you will see that that is exactly the case. Now, there is something interesting that happens in R. And so I really appreciate this question when it comes to you're talking about categorical encodings. And that is like when you split the data, it seems like the levels are maintained in your data frame, and you would have to like reset them. Maybe that is my ignorance, but regardless, you do want in tidymodels that is still removed, and you will see how that works. That was a great question. Thanks for asking that. Okay, all right, so this is a great framework. We're almost there, but so close, so close. There is one major point of consternation here, and there are a few minor ones that people are resolving, but there's a major one that's making us move into a better strategy for implementing this machine learning. Let's talk about what that is, okay? Let's talk about what it is. So again, we said that our goal of this resampling, right? Our goal of this resampling is to understand the performance of the model based on things it hasn't seen before, okay? So things it's never seen, doesn't know anything about. This, for all intents and purposes, is a test set, and the rest of these things here, so 2 through K, these are all the training set, okay? But it's still not quite right. Why? It's because of what we literally just talked about. So whenever we're training on these, actually, this fold up here, so let's say we're training on 2 through K, this fold 1 actually has knowledge of all these things from the whole training set. So it actually knows a lot about fold 1 already, based on the missing values, based on the normalizing of the data. It already knows things about fold 1 that it shouldn't. So now you're already biasing your K-fold cross-validation. Beyond that, there's also a conceptual problem with this, and it's that when you're doing machine learning, one should think about machine learning as a modeling process. So it's not just like a machine learning, a model learning this thing. It is like a process. The process involves all of these choices that you make beforehand. So you can't really just separate this and do it all this one time and then separate now your K-fold cross-validation. What you really need to do, I'll look at that. What you really need to do is put them together, okay? So now what you have is, instead of these being like 2 really separate pieces, you take this bit here, and we can call this a recipe. That word will come up again. We'll take this little bit here where you're working on the data to get it in a specific form, and we're going to actually embed this in the K-fold cross-validation or whatever resampling method you choose. So now what you really get is you get like training data coming into your cross-validation. You separate it into the folds. Now within each fold, you actually do all of these things, right? So it's actually making a lot of sense in terms of estimating parameters and having a really good sense, a much better sense of how your model performs and generalizes, because now you really have not really almost any information about anything you shouldn't. This knowledge about these folds 2 through K are completely separated from this first fold. So again, for that reason, we like to move all of this pre-processing into the modeling process. So this is a very complicated slide that makes it look very, very, very hard. So let's kind of simplify this just a little bit, okay? So again, let's call this building on the shoulders of giants, standing on the shoulders of giants. Borrowed this wonderful thing from tidymodels. This is a great great way to demonstrate the differences and what we're talking about in terms of pre-processing versus just model selection. So for example, this is a different workflow that we're talking about slightly. But what we have, again, is we have all of our data. So we have our predictors. And what we do is we do PCA. So PCA is a dimensionality reduction approach. And so a lot of people do this so they can have like some reconfigured data that is smaller. After they've done the PCA, people then go and do the k-fold cross-validation as one normally does on whatever kind of modeling that you're trying to do. So this is least squares. It can be any kind of estimation, so any kind of modeling. And then from there, you get the fitted model. So as you can see, the problem here that they're really talking about is that this is really a part of the modeling process. Like it's not something that's actually separate. It's decisions that are going to affect how your model performs. And something that they talk about in tidymodels in the book is that this right here, this PCA, if you put it outside here, you act as if like those quantities are known. Like there's like no uncertainty associated with them. Like they're just known and they are truth, but they're really not, because your model depends on what values that these are going to be taking on. So you really want to integrate this within your modeling process, okay? So do you guys, is that making sense? You have, what thoughts do you have there? I see some heads nodding. If you have questions, please feel free to drop them in the chat. Or unmute yourself and just ask. All right, things are looking good. I'm glad you're on board with
I had a question actually. So is part of the risk if you don't sort of combine it and sort of with the modeling that it could drop off, it could be forgotten or not done. Sort of what are some of the additional risks of not thinking of it as a single part of that workflow?
I love that point. Yeah, I think that is a lot of the risk in that, you know, you do. So whenever you go and you try to put this model or this framework in practice, or you try to evaluate how it performs, you don't think about the things that you said were actually like you treated them as true instead of treating them as uncertain. Like I think that introduces some amount of variance in what you should expect from your models at the end point. I think that's a really great point. Let's see. What parameters do you carry forward to the testing set as shown in the previous schematic? You guys have such great questions and comments. Like they're just amazing. Okay, so rolling back from Melissa's question, Brenica, I'm with you. In fact, my next slide is about the fact that mentally it sounds like it makes complete sense. Literally, it looks like we took a box that looked like this and we went like that. All it did is it just put another thing in the box. It makes sense. It makes sense to us conceptually, but the implementation is sounding really rough. Like, I don't know if you guys have used scikit-learn before or used like base R before, but the thought of implementing that is very difficult sounding, because not only now do you have to think very deeply about what you're actually like doing, but also how to set up the code so that it's flexible enough for when you want to use it the next time. And it's hard enough if you just want to do it this time. It's all hard. So it sounds very, very hard, okay? But as I said before, and as you have seen, I'm all about reuse. And in Python and in R, there are some great sets of packages that can really accelerate this workflow and help you to think about what you are doing instead of the minutia of trying to implement it. And so we're going to talk through what this will look like in both Python and with R. The way that it's implemented in Python is through something called a pipeline. So basically, instead of now having all these really like separate pieces, you kind of combine them all into one piece, one big thing, and it keeps track. So Melissa, it keeps track of the things that you need to estimate from the training set to apply to the test set. The same thing is present in tidymodels. So workflows are reflecting the same kind of information. What we're going to do is we're going to start with tidymodels because I feel like it's just more easy to understand. It will be straightforward to go from tidymodels over to pipelines, but the other way is a little bit harder. So I have a repo for you guys to look through. This repo does require that you already have RStudio installed and you already probably have an Anaconda install. You might be able to get it through Colab. I forgot to put the badge there, but let me stop share. Oh, well, before I do that. So we talked about how that image looked before, that it looked like super complicated, okay? But it's not really that bad. So let's look at what changed here, right? So we had our training data. Everyone here said we should split the data before we get started. Great, that's what we're gonna do. Take it, split it, great. But now, instead of having this separate pre-processing box, we have one big old box, which is now the machine learning box, okay? And within this resampling, we pre-process every single fold individually, okay? So every time we train on 2 through K, we're gonna pre-process our training data using these things, estimate whatever parameters, apply those parameters to fold 1, and then do prediction and get the performance. Then we do the same thing when we try to predict on fold 2. Training data, fold 1, 3 through 4. We do all these things again. We're imputing missing values or feature engineering categorical encoding. And then we we extract all the parameters that we used during pre-processing. We transform or apply them now to the fold that we're looking at, and we get the performance there. And we do that for all of our folds. So this is not so different. Again, all we did was it was just like the picture from tidymodels. We took that little bit, and now we just snap that right out. Okay, so then from there, what we do is, I kind of glossed over this a little bit because it actually introduces yet another layer of things that we should improve upon. But one thing that we can do while we're doing cross-validation is hyperparameter tuning. And so what we can do is compare across different hyperparameters using these different fold distributions of the performance. And so there is, again, just a little bit of consternation there because you would be using the training data to now test your hyperparameters on. And so that would present optimistic results in terms of what the best hyperparameter is. And so you don't really actually still yet have the best estimate of how your models are expected to generalize. And so there are ways to get around this. There are great ways to tidymodels. It's called nested cross-validation. You can implement this. But this is the way that I do tend to see right now the work being done. So do keep an eye forward. Nested cross-validation is going to be the way to do it in the future. So just learn about that. It makes sense when you read it. It's just another nested loop. But beyond that, you'll pick the best hyperparameters from these performances, and then you will get the training model, which then you will use here. Let's see, is that data leakage with hyperparameters? Yes. 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 Trying to think about how are we using the words data leakage. Yes, so we would be snooping. So we would know things about, no, I think this is more an issue of generalization. Basically, we're trained our hyperparameters on the same data that we're testing on. So it just results in a little bit of optimistic performance. Is it necessary that the individual fold sizes are in proportion to the test data? You might have to rephrase that one for me. It's necessary that the individual fold sizes are in proportion. If you're talking about like stratified splits, that really depends on your application. If you have like super imbalanced classes, it's great to do a stratification just to make sure the distribution of the folds is representing the distribution that would be in your actual data. I think that's perhaps what you're asking. Okay, all right, good. All right, let's see. So we're almost there, I think. So I think now we're transitioning over to actual coding. I'm very pumped. Let me know if you have any questions. I am excited to talk to you more about that. Oh, stop share. Okay. Okay. Great. So now let me share the repo with you. So you will be able to download it, and we'll give you a few minutes there. And I'll also show you how to do it in case you need to. Let me try to find it. Do you guys happen, Umang and Jesse, do you happen to have that in the Slack? I'm afraid to open the Slack.
I will get that right now.
Oh, let me see. I might be able to grab it. And data leakage. Data leakage occurs when you have access to information that you really shouldn't. For example, so yeah, I guess that question is correct with the private parameters. Anyways, but so the problem is that, so for example, with the, actually a great example is what happened like on Kaggle a really long time ago. So what happened on Kaggle was there was just some data set, and within the data set, there was just some column, and the column was essentially, like it was essentially the outcome data. And if you were to just use this column like as a predictor, you would get really, really great results because this column was present in the data set. And everybody was like, oh my gosh, we're like doing this great job, like everything is wonderful. But the problem was like that information should not have been available at the time of prediction. So that is kind of an instance of data leakage. Yeah, that sounds right, Peter. That's a good way to look at that. Okay, let me see. Let me click on this myself. All right, so I guess I can share here. Let me share again. See, there we go. All right, so this is going to be the repo. If you've come to our previous workshops, we've talked a lot about how to use Git and GitHub and how to get these things now from GitHub down to your computer so that you can use them. So again, this is the repo. It's called ML in Practice. We talked at length about how great it is to have like really good READMEs that are super descriptive. Just let your eyes casually glaze over as you look at this README. This is not an awesome one. It's not very helpful. We'll be talking about it today, and anyone who would like to contribute can feel free to do that. So basically, to tell you a little bit about this repo. So in case, whoop, I think our time. Okay, we have some time. This first notebook, so the scikit-learn, this is good. This is a Python notebook. So everything up there will be implemented in Python. And this is going to be your tidymodels notebook. Okay. And so that is the R notebook. Okay. So if you want to get this now on your computer, let's start with the R. What you can do is go to this code button, and you're going to click this little clipboard right here. It basically copies the address of this repo. So I should share my other screen now. Oh, could I zoom in? Okay, I can zoom in just a moment. All right, and now I'm going to share my other screen. Okay, so hopefully you can see RStudio, and if it looks a little different than yours, so mine is, I think it has the dark theme. And again, my computer is, there's something about it and R and Zoom, they just mortal enemies. Just give that a moment to catch up there. Give it a moment to catch up. But I am happy to describe how you can do this because I've done it just a bazillion times. One thing that, okay, so I think we're back. So we can come up here to File, and it's showing on the wrong screen, but you would scroll down to New Project and click on that. And then afterwards, it should pop up with some information about what how to start it. And it should, you should start it from a Git repo. So from version control. And after you start from version control, you can choose Git. After you choose Git, what you'll do is you'll paste in the link to the repo, and then it'll probably establish. So here we go. We're almost there. So I'm not going to go very far with this because as you can see, my computer is just, it's not about this life. So we're going to go to version control. After I click this, you're going to see something that says Git. And you'll click on that. Then you'll paste in the link to the repo on the next screen and just make sure that you know where that it has been saved. And then you will click OK or whatever the button is to make it happen. And it will pop up with the information that the things are being cloned from GitHub. So after that, you'll be able to see over here in the files. You'll be able to see tidymodels, ML workflows, and you'll just double click on that. And then you will see everything here. And again, I might have some problems here, so I will just try to talk you through it. If anything happens, we'll just hope for the best. I'm all about hoping for the best. All right, so does everyone have this sort of open? Can you give me a green thumbs up or put in the chat how we can help? We might not be able to, stop midway and, do a lot of debugging for everyone, but if there's something really like, if it seems like it's something very normal or weird that we would be able to figure out quickly, please feel free to send us a chat. Now, let me see, I'm looking for my Zoom box so I can see the participants.
Keep in mind, we'll have the recording available for this probably tomorrow. So you'll have an opportunity, even if you're not able to get something to work right away, you can simply follow along right now. And then a little bit later when the recording's available, you should be able to sort of pause, run, and then get this running.
That sounds great. That sounds like a plan. All right, so while you guys are thinking on that, I'll just talk you through this a little bit. So this particular section may take you some time to run. This is an installation of a lot of different packages. This is a package called Pacman, and it's just super great because I don't know if you've experienced this before, but if you have a bunch of library statements up here and then you give to someone else and they don't have those packages installed, then you have to go and back up package install, and it's so irritating. Pacman kind of automates this for you, so it's really great. Also, there's this register do parallel. This has to do with tidymodels. Whenever you are tuning hyperparameters with tidymodels, it likes to parallelize it so it can run a little bit quicker. If you run this line, it tends to run it a lot faster. It took me 12 hours to run something the other day, and it took me a couple hours to run today. So that was just really great. All right, so okay, so now that we have our packages, now that we're set up for parallelization, okay, we're gonna load the data. So we're gonna try to get the raw data that we talked about before. So we just load it up. We are using here the penguins data set just because I just really love it. I don't know why, I just really, really love this data set. So I grabbed penguins, it comes in this Palmer penguins package. And what we're going to do here is our goal is going to be to predict the sex of the penguin, giving its other distinguishing features. Okay, so we're going to, so first of all, we've printed out like basically a few columns or a few rows of the data set. And then we also have done this thing called skim. So let's just scroll over to the actual data set, just take a quick look. So this is showing us the size of the data as well as the number of columns. I really love this, and we're fortunate because we can already see that we're going to have to be doing a few things here. So first of all, we see things are factors. So these things might have to be encoded differently. We also see that we have some NAs, so it's looking like we're going to be doing some imputation. It also looks like, so again, we also have this gender thing going on. So then we can also use skim. Skim is pretty cool. Skim is pretty cool. It will tell you a lot about the data in general. So for example, it'll tell you the different types of data that you have, and then it'll tell you about each one individually. So it looks like we have some factors here. So again, your categorical variables. It'll tell you how many are missing and the complete rate and things like that. And it'll also give you the counts of these data sets of the top ones, which is awesome. You also have this functionality here. So these are the numerical data. It gives you like summary kind of information and also missing information. So this is great. I try not to really like overly delve into these things before I start splitting the data, but you just have to be very careful about the kind of conclusions that you make once you start looking at the data. So anyways, what we're trying to do here is we're trying to predict the sex of the penguins. And again, if that sounds really strange to you, it is a little bit strange given this data set. There's something much better that we can predict, which would be species. So cool. But I thought I would keep it simple by trying to predict something that's binary. And so this would give you a really good understanding of where to start and so where to go without the complications of being this multi-class classification. So we're going to start with sex. Okay, so we drop all the NAs there because how can you predict something that you don't know about? There are ways that you can impute the outcome, but use at your own risk. From there, what I do is I just tend to like to do a lot of sanity checks, and I like to check that things are as I expect them to be. So now that we've dropped the NAs in the outcome, what we can do is look at how many are left. and look at if there's anything missing, because we see that there's like 2 in these and there's not that many here. So maybe we drop the ones that had these. So we can see how that went. Up, looks like we did. So this is in missing. It looks like they're none. And we can also look at the levels, and this will come back up in just a second. Great. So what have we done here? We have loaded the data. We have dropped things that we would have dropped anyways because they are of no use to us. Great. So, all right. So then trying to remember the next step. What was it? Seems like it was splitting the data because we said, okay, we need to generalize. And again, I apologize that the screen is so small. Like the font on it is so small. I would try to make it bigger, but I fear our crashing. So just try to squint. And it's also in the GitHub repo, so you can look at it directly there if you like. But okay, so now we're going to split the data. And again, the purpose is that we're going to split so we can get the training separate from the test data. Golden holdout, we're trying to use it at the very end. Okay, so something really important that I guess we didn't talk about, but we will talk about during our reproducibility session, is that we need to set the seed. It helps us with reproducibility because a lot of these splitting is random. So when you get a really awesome model and then you run the code again and it's lost, you're sad in your soul. You could have also avoided that by splitting a seed or setting a seed, or at least outputting what seed was selected. Okay, so we set the seed, we do an initial split. These are tidymodels features, so tidymodels and tidyverse. In the image that I showed you before on the screen, on the PowerPoint presentation, you saw that tidymodels is actually a set of packages. So these are different functions that are coming from the set of packages. So initial split is about splitting the data. You can say that we're splitting the penguin data. Someone said to use a proportion of like 70 or 80. This is going to use 75. And someone else talked about stratifying the data. So we're going to stratify it according to the distribution of the sex. So perfect. I think the questions covered all that. So those are the data splits. Something that's interesting is that this is a split object. So there's further work that has to be done on it. There's further work that has to be done on it to actually get the training and the testing data. And the way that you do that is you use this really great word called training. It's a function that extracts the training data from the splits and the testing data from the splits. Something that you'll find about tidymodels and the tidyverse is that their creators were very, very passionate about code being readable. And I really love that about this. If you're thinking about what should be done, think about the most general word and then Google that with tidyverse or tidymodels. And that will probably be the word that would be used to implement the function. So this, we're going to be doing an initial split. Here, we just need the training data from the split. Here, we need the testing data from the split. So just think very generally about these terms. So again, as I said, I'm all about a good sanity check. We can see here, so the sanity check that I'm trying to do here is I'm trying to make sure that the sizes look about correct. So this looks like about 75, 25. It could be a little different with the stratification. But then I also like to just kind of look and make sure that the first columns are not like identical, or the first rows are not identical. Okay, those are looking good. Very simple sanity check in case I just need to make sure. All right, so now let's talk about this thing called a workflow. So this is what is enabling us to package things together into one reusable set of information. Okay, right? So a workflow is not just any singular thing. It's not just the pre-processing. It's not just the model. It is all of the things within your modeling process. And this is going to give us the power to expand our loop to contain the workflow. So not the feature engineering, not the processing, the pre-processing, not just the modeling. The workflow is the thing that we're doing our cross-validation and our training on. Okay, so how does this look? So I've included some words here just for you. So whenever you go and look at this again, you'll know what we were talking about. It's a great literate programming practice. But something that's so awesome about using tidymodels is this use models package. And so it gives you some kind of pre-baked template code to be able to run so you can get some basic understanding about what you should be implementing. Okay. So use models is basically going to give you, again, template code for a specific set of models in the tidyverse, right? And so, for example, I am going to be using use glimnet. So it's a GLM, generalized linear model, net. It's referencing the type of regularization that's possible. And what we're doing is we're going to specify with a formula what we're trying to do. So we are trying to predict sex, and that is going to be distributed according to all of the predictors. That's what that dot is. All of the predictors in some data set. Then we need to tell it what data we're looking at. And that data that we're going to be using is called trained data. And that's a trained data that we made just a little while ago. Okay. So after you run this, it just dawned on me that I have not told you once how to run this. So if you want to run this, what you can do is go over here and click this green button, this green arrow. That'll run the chunk. Also, you can click on anywhere within a chunk and click Control-Shift-Enter. And that should be able to run the things. Okay, so then after you run that, whoop, my computer. Okay, there we go. We made it. We made it. After you run that, you should see this kind of information pop up. And this is the great template code that we were talking about. Okay, but what is this? What is this, right? Wonderful. I'm glad you asked. Okay, so remember, we were talking about the pre-processing, right? And we said there are some different things that you might have to do. So for example, you might have to normalize, right? You might have to normalize your data because you're using maybe something that needs normalization. You might have to remove columns that are just completely constant in your training data. You might have categorical data that you need to make into dummy variables. You might have things that you need to make new categories for. So if you expect that maybe your training data won't have all of the different categories, you might just have one that's like everything else. You might want to do that too. So you also might want to specify what you want to do those for. So we could create categorical like information for all of the categorical data, but not our outcomes, right? And so categorical data is going to be your nominal data. We could also remove any predictor columns that are constant, right? So we would want to remove all from any of the predictor columns, anything that has zero variance. And we want to normalize all the predictors except the ones that are nominal. So this recipe part, that might look really familiar. It looks a lot like that box that we had a second ago that said pre-processed data. So that is a lot of what that is. It's a lot of pre-processing and it's a lot of feature engineering on the data. There's a lot of things that you can do within recipes. And I encourage you to look at the recipes package in tidymodels because it'll tell you about all the things that you can do. It's fantastic. Okay, so this is part of the picture. This is part of our new training loop, right? This is part of it. The other part of it is our model, right? So what kind of model are we going to use? Well, here we can use a logistic regression. I told it that I wanted to use LibNet. It popped this out. Perfect. Logistic regression. Great. The logistic regression has a couple of hyperparameters that we can do, two of which are penalty and mixture. So this is how strong the regularization is and what type of regularization you're applying. So something that's really cool about tidymodels is their hyperparameter tuning capabilities, right? So this says tune, right? What does that mean? What is that? So in real life, in probably like how you're thinking about your classes, you would set a penalty. So maybe your penalty would be like something super low, tiny, because you want however much regularization that you want. With your mixture, you might set something maybe super low. I don't know. Maybe you want whatever you want. Maybe you want L2 regularization. Maybe you want L1. You would set those to be numbers. But we actually don't even know what the number should be, right? We have not really that great of a clue. We have some idea maybe, but we don't have the best idea. So what tidymodel says is, that's fine. You don't have to know everything. This tune thing right here, this is basically us taking a knob and just sticking it where that number should go. Just got a little knob there now. And so instead of you putting a number there, all we're going to do is we're just going to be turning things. We're just going to be turning the knobs and putting in values. We also set the rest of the parameters for the logistic regression. So logistic regression that we're going to be doing is going to be doing classification. And we're also going to set a backend engine called LibNet. There's lots of different engines that you can use. I know that there's some statisticians here. You might be able to use your favorite one, but there's several that are already available through tidymodels. Okay, so remember, the two things that we kind of put together in the same box were the pre-processing and the feature engineering, and the model specification itself with the hyperparameters that we wanted to tune. What is this workflow then? Man, it's looking really familiar. Wow, it's exactly that. It's the recipe that we just made. Yep, that box that we had with all the pre-processing and the feature engineering. And oh my goodness, the model with all the tuning that we had. And we're putting it right into a workflow. So basically, now if we were to iterate over this workflow and have the workflow as the modeling process, and that's what we could tune our hyperparameters on, we would have achieved our goal. This is tidymodels. This is why it is arranged like this, and that is the exact purpose. Okay, so now that we have our training loop pretty much specified, our machine learning workflow specified, okay, now we want to talk about what exactly we should put into these little knobs. Like what should be the bounds on the knobs, right? We can tell tidymodels how we want to do that. These are just sets of values that will be put together in a crossing that will be tried together. So for example, like 10 to the -6 will be combined with like 0.05 and so forth. And those will be the sets of values that you'll try in your grid. So this just specifies a grid of these different values that are combinations. And then our next step is actually to do the tuning. So this all came out of LimNet. What you need to do is copy and paste that. So I copied it here, then I ran it again, click that. And so this saves the recipe. This might be a little frozen. We're going to try to make it. Oh, I'm sorry. Okay, so we might, okay, nope, we made it. All right, so, oh, went too far. So then I copied and pasted this as well from the template code, and you can see here the same things. So this is an interesting point now. Okay, so we didn't talk about this before, but we actually need to specify what the cross-validation folds are. This didn't come out of the used models. This is something that we need to specify ourselves. Why? Because our hyperparameter tuning grid is working on the cross-validation folds. So we need to say what the folds are, right? So this is a function that generates our cross-validation folds. The creator of tidymodels really likes to call it vfold CV. He feels that like K has too many other associations, so vfold. And what we're going to do the vfold on is only the training data. So here we specify training data only. This helps us to avoid errors. We're going to set the number of folds. We want it to be 5. And as someone said before, we're going to stratify as well. So now after we're done running that, we can get the cross-validation folds. If we wanted to just take a look at what they look like, it's a split object. This is what all the splits look like. So there are 5, look for the figuring. Okay, just a second. So there are 5 different splits you can see here, and they all have this analysis, an assessment, and a total. So here you can see like the different folds that are used for training versus the folds that are used for testing, and then the overall. So this is our K fold, our V fold cross-validation. So now we've made that. Okay, so this is the grid that we had before. So this is the same thing. Okay, it's not the same thing, but it's the same concept of what just came out of used models as a template. This is just a slightly different way of doing it that is just a little bit better. What times? Oh man, I need to hurry up. Okay, so this is a different way that is available through something called dials. It's another package. And what it allows you to do is set a grid of hyperparameters, a number of them. So here I'm using 5, and it sets the grid according to this max entropy kind of formulation. And so what we do is then we start tuning, right? So this is where we're doing our K-fold cross-validation on all of any of the tunable parameters in our entire workflow. So the tunable parameters that are available in the model, and also making sure that we're taking into account the pre-processing that we do during our recipe. So here we're doing the tuning. So here's the workflow again. This is
can I ask you a question too?
Sure.
So before, when you specified the grid, is it fair to call that sort of a brute force way where you just sort of check it at those sort of intersections? And this is sort of a search, a more informed search of your hyperparameter space?
That is a great way of phrasing that. That's a great way of phrasing that. And there are also some other different methods that are available through, I think it's dials. I put dials here, but now I'm not sure. There are a lot of different methods that are available. There are Bayesian methods available, randomized methods. There's lots of different ways available that one can generate their hyperparameter. So that's a really great point. Okay, so now we have our workflow that we can tune, and now we're actually going to tune it. So tune grid. And what are our options there? So the resamples. So this is our resampling strategy that we talked about before. What resamples are we using? Cross-validation fold. Okay. We also said that we're going to be doing some hyperparameter tuning. Okay, what are the hyperparameters that we're tuning? This grid that we talked about. Great, perfect. We also said that we need to figure out how the models, cross-validation models, perform on their separate test sets. How? Well, with metrics. And because we're using tidymodels, which has the yardstick package, yardstick has a great number of metrics that are implementable and understandable. So we just pass in something called the metric set, which is an aggregation of a lot of different measures, anything that we care about and can implement. Then we also have this parameter called control. Control basically is just used to tell you things about the model or change certain things about the grid. And you can look more into that into the modeling. So I was so excited to see that this ran for me in 14 seconds. That was super exciting. If I ran it right now, it would take 13 years. That's okay. So now that we have this tune grid, and keep in mind, this actually performed the tuning. Okay, so this performed the hyperparameter tuning. So that's stored in this object called glimnet_tune. And what we can do if we just want to look at it, so you don't have to do this, but you should. What we can do is we can reconfigure that just a little bit, and we can pop out the actual fold metrics. So for example, this is fold 1, and I've done a head here, so this is much longer than just 10. But this is fold 1, and you can see all the different metrics here. And you can see you can start to see like the different models that were run on fold 1. And you can also see the actual estimates of all the metrics for each of these models. So you see this is model 1, this is model 2. These are all the metrics for model 1 and their values, hyperparameter values, as well as their estimates. This is in tidy form. So if this looks very, very unfamiliar, we can go learn a little bit from tidyr about what this representation means. Okay, so these are our metrics. They're all separated, but tidymodels offers a really great function called collect metrics, which does some averaging over all of the folds. I just gave up there, saw that. So then we can get the average performance for each of the folds in terms of each of the measures. Then we can decide on exactly what measure it is that we want to select the model based on. So for example, maybe we really like AUC, ROC, and that's really important to us. Well, if that's the case, what we can do is we can select the model which has the best ROC, AUC over all of its folds. So for example, we can show best in terms of this metric, and we can see the best of all of these. We can also select the best one. And when we do that, we can select the best and we'll get the parameters, which are now defining the model, right? So now that we have those parameters, that defines a lot of what's going on in the model. So we select the parameters and then we update the workflow. And then using that workflow, again, recipe, feature training, pre-processing, and model, those two things together, we take that whole thing and we fit it using the training data, okay? And now we have our final fit. So here I printed out like the workflow before the fit for you to see. You can see here that it tells you all the things that you've done. So in case you ever need a sanity check, you can print things out about what you're doing. It tells you about your penalty. It tells you about the mixture. After you have it trained, then you can start looking at the performance. So I like to look at the cross-validation performance. So this is what I find this is what we should be using to understand how our model is performing and comparing them to other models to choose. So for example, this is how the best model looks in terms of distribution. And you can consider this and think on this and ponder on this and what it means a little later on, because we're running at the end of the time. But when you do look at these confusion matrix metrics, do think about what Jesse talked about in terms of metrics last week, that these are just at one single threshold, these negative predictive value, positive, like these are at one single threshold. And if you were to change those, then these results would be ever so slightly different. Not ever so slightly, but they would be different, period. These would be the same regardless, except for that. All right, then we can look at the training data as a whole. So I said, again, that I always look at this because I like to see how the model does in general on itself. Like if the performance is already bad on its own training set, then it's probably going to be a pretty rough model. So I just look at it just to make sure that it's not. And so it's doing pretty well on its own, what it was trained on. This is pretty good. This is pretty good. And we can see that the performance is okay there. But the cross-validation metrics tell us a lot more about how we can expect it to generalize. Okay. Lastly, I love variable importance. I passionately love variable importance. And so I always take a look at that, love it. What it does is it tells us now about which models or which features were most important in the prediction, as well as the direction of their prediction. So for example, we have these, so scrolling back a little bit, we were predicting was the sex of these penguins from this different information, right? So you can see that the dummy variables have been made here. You can see the original information here. So Bill life, and so you can see here now that this is the strongest predictor, and it's very strongly related to predicting male. And you can see kind of the distribution of those here. These ones are like, these two are like super important. These three are having the same importance but less, and then these are like, so this also can help you understand if your goal is to make a parsimonious model, meaning that you want like the fewest number of features possible, this kind of information can help you understand that. Okay, so this is a very important question, and it is, how do you know exactly the order or the target class? So for example, if you were going to right now calculate sensitivity, you would have to do it by calculating the number of true positives. But which one of these two is the true positive? Which one of those two is positive? Like, how do you know which one is the one that is the positive data or the positive level? Okay, there's some consternation. We don't know. That is actually a very hard question. It's very, very hard. And I was going to scroll up, pushing it. Okay, Daniela, I love that idea. I think you're with me on the sanity check idea. So one thing that I always do, so it's this is where I do my sanity check, because I look at the confusion matrix and I make sure it matches the expected sensitivity and specificity that I'm expecting. So if I think that the positive class is female, I should be able to calculate this and it give me exactly this value. But beyond that, we can also look at what the positive class is, in the sense that we can look at the levels of the data. And so I did that at the very beginning, and I told you about it just a little bit because we were going to come back to it, because it's really important with tidymodels. Tidymodels is something really interesting, especially with yardstick, in that the positive class is actually the first class. For most, not most, but for many like metric calculators, the positive class is the second class. So that's something that you have to be really, really careful about with tidymodels. Just make sure that whenever you're doing your computations and you are, thinking about your model, that you are understanding what is being calculated. So keep an eye on that as you're processing. Okay, so we are kind of at the end here, but I am going to go through Python very, very quickly. And the reason that I'm going to go through it very quickly is because we've already talked about tidymodels. If you have questions on what's going on in scikit-learn, go back and read about what's going on in tidymodels, because it's like they're spelling it all the way out for you in the book and in their tutorials. And you know what? We'll send you some information about the really great tutorials that they have, as well as where you can read the book. Okay, so last piece, very quickly. Okay, let me share the screen. Ooh, maybe I can, I'm gonna close R.
And while you're doing that, one thing that is kind of interesting to know about tidymodels is that is Max Kuhn's second modeling framework. So he had a do-over. He did Carrot early on, and he realized that he wanted to have a good, meaningful approach to modeling. And so tidymodels came out of that. And that's why it's so, in my mind, so clean. And why it's a great idea to start there. Even if you're going to be doing Python, read the tidymodel stuff. And then, oh, looks like you're up. And then do scikit-learn after that.
Such great advice. It is such great advice. All right, let's see. So if you, I guess I don't, okay, so I don't think that I have time to show you how to start this. So I think I just have to run it. If you're familiar with Jupyter Lab, this is the ID that I'm using. But for now, just follow along. And if you have questions, you can feel free to reach out. So this has a lot of different packages that we use. So mostly the regular data science packages, as well as scikit-learn, and some different things from them. And so what we can do is we can go ahead and read the same penguins data set This is a probably not the best way to have read this because it's reading directly from the CSV. I think there are packages available that allow you to step away from that. But I did this just to make it very quick and easy to understand what we're looking at. So it looks like my computer, okay, we made it. So now this is, you can see this is the same data that we had before. We can also see that again, we're going to have those same NANs, right? And so we can also see the same information again that we had kind of from Skimmer about what is null and what's not. So love that. We're going to do the same thing that we did before. So we're dropping in A and we are looking at the dimensions for a sanity check. Okay, it's looking really familiar. Great. Now, again, doing the same thing we did before, setting a seed, looking at this particular column. The interface is a little bit different, but you can see that we're stratifying according to the outcome class. So now we're going to split it into our different chunks. You can see that this one really wants you to split it into X and Y, which is very interesting. I don't want to bias you towards whether that's good or bad, but it's something. So now we can do a sanity check. And we can see that this is looking about right. We can see the sizes are looking about right. And we can do a sanity check on the outcome variables. We can see that they are the right variables. So it's male and female. And we can also see that their indices are lining up with the ones in the training set. So this is 101, this is 101, 260, 260. So they're aligned. This will make you feel really good. Good. Love sanity checks. Whoop. So this is where we start getting into the differences between tidymodels and scikit-learn. So they're very similar now, but there are some differences and there are some things about tidymodels that make it a lot easier than scikit-learn. So for example, we have these different pipeline steps that we need to do. So we said before what we had with tidymodels was a workflow. Here we have a pipeline and we need to kind of create pipelines of pipelines to define the final pipeline. So for example, here we have a pipeline, okay? This is where we're going to be processing our categorical data. So the name of this one is going to be imputation. So we're trying to impute the values for our categorical variables, even though we actually don't have any missing ones. And here we're going to one-hot encode and drop one of the levels of its binary. So that's now, after we run that, our categorical variables should be fixed. Then we need to do something slightly different for our numerical ones, and we're still going to impute, and we also need to scale. Okay, that's great. So those are two different steps in a pipeline that would correspond to different columns. Therefore, now we need to aggregate those into a column transformer and make sure to say, hey, on these specific columns, I want you to do that pipeline. On these specific columns, these numerical ones, I want you to do this other pipeline. Wonderful. So now we have all of our pre-processing. Great. We have one chunk of it. With that pre-processing, we see that here, this is that pipeline. We put it together with our modeling, and now we have one big pipeline, again, that forms our modeling process. Okay, so now we are still at the same point that we are with tidymodels. Now, there are some advantages to scikit-learn here, and it's the way that they've implemented this. Like, it looks like super hard, and it is a little bit more challenging, let's be honest, but they have made it so great to be able to change hyperparameters in the steps that are up here. Like, it is so great. It's so great. Okay, so anyways, so now we need to define the different values that are in our tuning grid. And you saw with tidymodels how that looks kind of straightforward. This is almost trying to be straightforward. So here we have model. So this references the logistic regression. And these are actual parameters that you would pass into logistic regression on itself. But then instead of passing in just one number, like we did with the hyperparameter tuning on R, we pass in a set of values. So here we just pass in some values, 5 values between 0 and 1. This is the other parameter of our logistic regression. We use a log space, so it's kind of the same thing, but on the exponential scale. And that will be our tuning grid. And so now we do a grid search. So the same thing that we had before, tune grid. This is grid search CV, cross-validated. Again, we have the same sorts of parameters. We're telling it what we want to operate on, right? So we want to operate on our workflow or our pipeline in scikit-learn. We want to do a tuning grid. So we need to tell it that. We need to give it our cross-validation folds. And this is just a special parameter that allows us to look at the actual outputs of the cross-validation. Did I run that? No, I did not. Okay, run this. Then, then actually we need to run this fit. So fit actually is like the same fit that we had before. So now we're fitting the model and the pipeline. We're struggling a little bit, but we're going to make it. And here, after we're done with that fit, we can actually look at the best score. Okay, so we can look at the best score and the best parameters here. So here we have fit with the best thing, and we can see here that the best thing here, pull that up. This is the best score that we have. Careful about this. You can pass in different metrics, but this right here is going to be the accuracy. This is okay for us here because the sex is kind of balanced. And then here we have the best hyperparameters that we have picked from our model, and there they are. Then we can look at the cross-validation results. For me, I find this very easy to work with, so great. The only problem is that it's relatively long or wide instead of long, which kind of can make it hard to plot. It's okay. Then we'll do look at our final fit because we've actually already done the final fit. After we do the cross-validation, it's already identified. So here we have our best estimator. You can see the exact values that we had literally 1 second ago that we were just looking at. And we can also, again, look at the variable importance. It's a little bit more challenging once more. Here again, we can see our levels for the same reason that we had it before, except for with scikit-learn, it does use a second level like normal, so you don't have to worry about that. But with logistic regression, it wants you to specifically look at the coefficients instead of using an interface like variable importance, which is so annoying, but it's okay, you make it. And you can actually see here something that it makes me very excited. And it's that these results actually match very closely with what we had in tidymodels. The difference that you would see would be this Adeli column. And you can think about why this is. It comes back, I believe, to something that Mahmoud asked about, which is about the encodings. Tidymodels will take out a specific encoding if it's not there, and also there are different splits. So you can look into the actual reason, but I have 2 suspicions about why that's there here and not in tidymodels. And it's probably mostly about the splitting of the data. It's present in the trigger. Lastly, you can just look at a really great aggregation of the classification metrics. There's great functionality there, and it can tell you about the overall performance. But this is going to be on the test data. So now we're at our last moment, and we're like, okay, this is the model that we're going to pick. This is when we'll be doing this, and it tells us about our performance. Something that I like is that this is like separated like this. And so we can learn about each of our classes, which is kind of just normally how it is. But this is a great opportunity to look at fairness in models. So if you see that you have really differential precision and recall or F1 score between your 2 classes, and your classes happen to be things that will affect people if your model is differential like this, it's a great opportunity to look at how you can improve your model to make it more fair for everyone that would be the recipient of its usage.
Is there a way to do that in tidymodels?
I believe that there probably is. There probably is. I haven't quite used it yet. All right, fantastic. So I think we're here at this last final minute. Thank you guys for joining me today. You guys asked such great questions and had such great comments. Thank you for joining me. Please feel free to reach out to me if you have any questions. You have the repo there. I believe you can add issues, but if you can't, you can always send me an email. I'm happy to work with you further. And I think I'll be here for just a few minutes in case anyone has any questions. But thank you for coming.
I'll go ahead and I'll allow you to unmute yourselves. Feel free to unmute yourself and ask questions. So Sharo Mahmoud asks, in practice, is tidymodels comparable to scikit-learn regarding availability of algorithms community support?
That's a really good question. I have just been working with tidymodels so much lately that I'm like biased a little bit more towards tidymodels. From what I saw with scikit-learn, it looks like, so number one, tidymodels has a whole book by the creators. And I think that speaks volumes kind of about the kind of support that you're going to be expecting with tidymodels. But scikit-learn, I think it's okay. In terms of availability of algorithms, maybe it might be a little superior. In terms of maybe statistical models, not so much. And statistical, perhaps rigor of those models, maybe not so much. But the community support, I think, would be stronger in tidymodels. It's a good question. How do you choose the number of folds? Oh my gosh, that is such a good question. I would not try to tell you how you should choose that, but that book that we talked about by Max Kuhn, it goes over like choosing the number of folds and choosing your resampling method. And it's just really great for understanding that whole framework. I think a lot of it right now is like rule of thumb and what we normally do, but in terms of things that are outside that, Max does a really great job at explaining that.
Peter had a question on when you would use GLM versus linear regression model. GLM is actually just a more general statement of regressions. So it includes linear regression models, but also includes logistic regression and a bunch of other things as well.
All right. Fantastic. Well, we have to run off to another meeting, but thanks again for coming, and I hope to see you again next week.
Yep, come back next week. I'll be presenting on deep learning models.
Bye-bye.